everyone. Thanks for clicking. Don't forget to hit that subscribe button. Today we're going to talk about why we individually calibrate each and every one of our meters, and you get to get a little bit of an electrical engineering background.
Okay, this is David from 9CI, and today I'm going to give you a brief overview of why we calibrate every single one of the meters that comes off our production line. So, why RF meters require QUIRE calibration. Okay, so an RF meter is basically made of these components. You have an antenna, you have some measurement, RF measurement, then you have this is a power level output. Then you have an analog to digital converter. Well, I'll talk about what each of these blocks are. And then you have a processor. And then you have a display. Okay. These parts are often in the same chip, called a microcontroller. All right, so why do you need to calibrate your RF meter? Well, your RF measurement chip takes some power level. You have your RF coming in, and it's some sort of waveform. It measures the amplitude of that waveform, and then it converts it. So on this side it's AC. On this side you get a DC output going to your microcontroller. And it's some voltage level, and it goes up and down based on the amplitude of the AC input. So this would be the amplitude of your RF. Now, most RF measurement chips, most amplifiers that are a monolithic chip, they have some sort of internal temperature compensation. It's built into the amplifier. So that's really cool. That means basically for a given amount of RF in, you'll get the same amount of DC voltage out. Okay, so this part is pretty good across temperature. But that's only part of your meter. All of your digitization happens on the other side of this line. This is where you convert the signal to a number. So your analog to digital converter right here, that takes an analog signal, like a DC level, and it turns it into a digital signal here. I'm just going to write through here. This would be, it's often referred to as a DN, or a digital number. Digital number. So, let's say we have like 1.67 volts DC into our ADC. That would translate to something like a 512 digital number. Okay? Or if we had 3.3 volts DC, that would be something like 1023 as a digital number. Bigger voltage, bigger digital number, smaller voltage, smaller digital number. And of course 0 volts DC would be 0dN. So, your RF amplifier converts your RF signal into a DC level, but all of your DC level conversion to the display value, all of that happens to the right of this red line. This is the part of the meter that we have to calibrate. Not optional if we want good measurement. Why do we have to calibrate this? Well, for one, the microcontroller usually doesn't have temperature compensation inside on its measurement subsystem, like this guy does. The other reason is this chip, this microcontroller, the dotted line here, it has its own power supply. Out here we have our batteries. This is what batteries look like for an electrical engineer. That's 2 batteries. So there's power coming in here. Let's call it 3.0 volts. It's a couple AA batteries. It comes into a power supply subsystem. Let's draw that here. PSU. Okay, there we go. 3 volts into our power supply. And then of course it's tied to ground as well. Our power supply, if it's good, and we use a hybrid power supply on the safe and sound line, so we use a boost regulator on the 3 volts to raise our voltage up to a stable value, and then we put what are called high PSRR, I'm going to write it down, high PSRR linear regulators on the output of that boost regulator. So PSRR stands for power supply rejection ratio. So these are basically, they reject any noise that's on the supply. So they give a really clean, very stable signal. They're designed for RF measurement equipment. We use that on all of the safe and sounds, the Classic and the Pro. So we get a voltage out from this. Let's say it's 3.3 volts in this case. And it goes into our microcontroller here. 3.3 volts into our microcontroller. So our analog to digital converter and our processor run on this 3.3 volts. Well, these power supply chips, while they are very low noise, are not internally, they have some internal temperature compensation, but it's not ultra super high precision. And we're trying to measure very small values here, so we need high precision. So basically, if the temperature of this power supply or the circuit board goes up, the output voltage here, this 3.3 volts, it might become 3.31 volts or something like that. And if the temperature goes down, it might be something like 3.29 volts. It can vary a little bit. So, and there's manufacturing variability. You know, if we're making thousands of these things, not all of them are going to have exactly 3.30 volts output. There will be a small amount of variation that's defined in the data sheet for these parts. There will be a little bit of variation in the analog to digital converters. Again, it's defined in the data sheet. And you get stack up. All of these small errors for all of these components can stack up. So how do we deal with that? Okay, I'm gonna use a new space here. How do we deal with that? Okay, what we do is we do 2 things actually. The first is we do a, actually I'm going to keep going with blue. We do a 0 RF cal. 0 RF cal. This will be item number 1. 0 RF cal. So what we do is we take the entire unit, we take the whole subsystem. We have an RF quiet environment downstairs on the assembly line. We have a metal shielded enclosure in that RF quiet environment. We put the entire device in that enclosure, close the lid. We have a software subroutine that takes a bunch of samples. It takes a bunch of analog to digital converted samples from our RF amp and establishes a baseline for when there's 0 RF, when it's in a totally quiet environment. What is the digital number that comes out of the analog to digital converter in that environment? So that gives us 0 RF cal. Then the other thing we do dynamic temperature compensation. Okay, so we have a 0 RF cal. Let's imagine a scenario where our unit, our safe and sound, is sitting on the dash of our car. Okay, it heats up. It heats up a lot. Let's say it's at like 40 degrees Celsius, or I don't know what that is, 90 or 100 degrees Fahrenheit, something like that. This output voltage from our power supply might move around a few hundredths of a volt. That's going to shift the measurement reference for this analog to digital converter. So when it sees a voltage level from the RF amplifier, its reference level is here. If its reference level changes, it's measuring everything relative to its reference level. So if its reference level moves, it's going to see a different value because the relative voltage level between the input and the power supply has changed a little bit. So what we've done is we've taken the entire device and we've taken it from about negative 15 degrees Celsius to about positive 50 degrees Celsius. And we've figured out what the characteristic offset curve is. So we figured out how does the measurement change across that range of temperatures. And then inside the processor, we have a temp sensor. Temp sensor. We have a temperature sensor, and every 3 seconds we measure the ambient temperature of the device, and we run our correction algorithm to adjust the measurement offset to what the correct value should be at that temperature. So, dynamic temp comp every 3 seconds. So if your device is really hot and you pull it off the dash of your car and you turn it on, as it's booting, when it's doing its self-calibration, it's going to look at what the temperature is, and then it's going to adjust the measurement offset to the new 0 cal value at the ambient temperature the meter is at. This has nothing to do, or has very little to do with the RF amplifier. It mostly has to do with the rest of the system. You have to temperature compensate this stuff too. But because we've actually done our temperature compensation on the entire device, the whole enchilada, even if we have temperature drift in our RF amplifier, we calibrate it out. And this happens all the time while the meter's running. You don't have to do anything. It's just taken care of automatically. The other thing that we do, which is actually up here in the 0 RF cal, we measure temperature. Measure temperature while we are doing our 0 RF cal at the factory here. So this value is referenced to a reference temperature. And so that's what pins us down. You know, here's our temperature compensation curve. This would be our calibration point, cal point. So we know that 0 RF on this axis is here, and we know that this is the cal temp here. 0 RF calibration temperature puts us on this line. Then if our meter heats up, we shift to a point up here. If our meter cools off, we shift to a point down there. Anyway, this has to do with all of the rest of the subsystem. Even if you have a temp compensated RF measurement subsystem, you have to temperature compensate and calibrate the rest of the device because there's all these other variables that affect your measurement. Now, this is only an issue if you're trying to measure with high precision. If you're not trying to measure with high precision, you don't need to do this. But if you're not trying to measure with high precision, then you're talking about, you know, a lower end device. You can buy these $100, you know, $50 devices, and they won't do any of this stuff. But when you start spending real money on a really good meter that measures precisely, the meter has to do this. Otherwise, your values will not be accurate across temperature. They won't be accurate across, you know, different measurement conditions, and they won't be accurate between meters. So you have to do RF calibration on every single meter that leaves your factory.
Thanks for sticking with us. Hope you enjoyed that and found it as informative as I did. Please feel free to subscribe to our channel and follow us on SoundCloud and leave some comments below. Let us know how we're doing. Talk to you soon.